Welcome back. We will finish this week with two lectures 4 and 5. These two lectures describe some theorems concerning subsequential limits. The content of these lectures are contained in pages 71 through 76 in your textbook. If you wish to see a different presentation, in this lecture, we will describe three general theorems on subsequential limits. The first explains what happens to the subsequential limits of convergent sequences. The second is a structural theorem. It says that given any sequence, the set of all of its subsequential limits is a closed set, in the sense defined in the previous lecture. The third reconnects the behavior of general sequences to that of monotone sequences. Let us begin. The first theorem is somewhat obvious. If a sequence converges to Z, then all of its subsequences converge to Z. Or, in other words, a convergent sequence has a unique subsequential limit. We have already seen a similar theorem earlier. We proved in a lecture last week that if a sequence converges, then the lim sup and lim inf agrees. This theorem is in a similar vein. The proof is pretty simple. Since x converges to z, we know that for any epsilon positive, there is a natural capital N, such that for all further indices, x sub n is no more than epsilon away from z. Now, let x sub n sub k be any subsequence. Since n sub k is increasing, we know that n sub k is at least k. Remember, you can skip values when you count for the subsequence, but you cannot reorder or repeat values. Therefore, for every k that is bigger than capital N, we know that n sub k is bigger than capital N also, and hence the x sub n sub k is no farther from z than epsilon. So this means that the subsequence x sub m sub k, regarded as a sequence with index k, is also converging to z. The next theorem concerns the set of all subsequential limits of a given sequence. Let S denote the set of all subsequential limits of a sequence x sub n. Then, the set S is a closed set. This theorem puts severe limits on what can be the subsequential limits achievable by a sequence. For example, in the previous lecture, we discussed how the open interval is not a closed set. This means that there cannot in fact be a sequence whose corresponding set of all subsequential limits is exactly the open interval from 0 to 1. This theorem also allows us to potentially discover new subsequential limits given old ones. For example, suppose we know that a sequence is such that every z strictly between 0 and 1 can be obtained as a subsequential limit. This theorem then tells us that both 0 and 1 should also be attainable as subsequential limits of the same sequence. So how would we prove such a theorem? We need to show that if S sub m is a sequence whose terms are each subsequential limits of x, then all subsequential limits of the sequence S are themselves subsequential limits of the original sequence x. This part can be a bit confusing since we're doing with two levels of sequences and two levels of limits. We have the original sequence x sub n. We have a new sequence S sub m. Each of the terms is a subsequential limit of the original sequence x sub n, and we have z, a subsequential limit of s sub m. We want to prove that z is also a subsequential limit of x sub n. Before moving on from this slide, please pause the video to make sure you understand the logic. If not, feel free to ask on Piazza. Before writing down the proof, it is illustrative to see what actually is happening pictorially. Here, I drew the real number line in white. In blue, I denoted the point z. Our hypothesis says that z is a subsequential limit of some sequence s sub m. So here I drew the subsequence s sub m sub k, which converges to z. A particular consequence of this convergence is that if we draw an interval with 2 epsilon centered at z, there are infinitely many terms of the sequence s sub m within this interval. Now, let's zoom in a bit. Here's again the with epsilon interval that we drew before, but blown up. As we discussed, there are infinitely many elements of s sub m nearby to z within this interval. So certainly there is one, at least one. This we will call s sub capital M. Now, we remember that every term of the sequence s sub m is a subsequential limit of the original sequence x. Remember x? This means that there is a subsequence x sub n sub l that converges to s sub capital M, which we now draw in orange. Since this subsequence converges within any interval of width 2 delta centered at s sub capital M, we can find infinitely many terms of the original sequence x. Now, if we choose the delta judiciously, we can guarantee that this interval with size twice delta is entirely contained in the interval with width twice epsilon with z as a center. So this means that within distance epsilon of z, we can find infinitely many terms of the sequence x. And this means that z has to be a subsequential limit based on what we discussed in lecture 2 of this week. Notice that the size of the interval delta needs to be adjusted depending on where s sub capital M is. If s sub capital M is closer to the edge of the epsilon width interval, then we have to choose a tiny delta to make sure that the delta width interval is entirely contained in the larger interval. Okay, so that's an overview of the proof. Now let's write it down. Evidently, those pictures from before were not worth 1,000 words, since the proof, once we sort through how it goes, is not very long. Step 1, I re-announce what we need to prove in order to show that S is closed. In step 2, we take Z to be a subsequential limit of the sequence S sub M. By Theorem 52, we know that there are infinitely many terms of S sub M within a distance epsilon from Z for any positive epsilon. So we just choose one among this infinitely many and call it S sub capital M. Now we make our choice of delta. We set delta to equal exactly epsilon minus the distance from S sub capital M to Z. Since we know the latter is strictly less than epsilon, delta has to be positive. Using that S sub capital M is a subsequential limit of the original sequence x sub n, there are infinitely many terms of x that are no more than distance delta from S sub m. We next apply the triangle inequality in step 5 to compute the distance from a term x sub n to z. This, by the triangle inequality, is no more than the sum of the distance from x sub n to s sub m and the distance from s sub m to z. For the former, it is strictly less than delta, provided the index small n is one among those whose terms are within delta of s sub m. Since delta is chosen to be epsilon minus the distance from s sub m to z, we see finally that by this computation, the distance from x sub n to z is less than epsilon. Hence, each one of the infinitely many terms of x that are within delta distance of s sub m must also be within epsilon distance of z. And this shows that for any epsilon positive, there are infinitely many terms of x closer than epsilon to z. And by theorem 52 again, we conclude that z is a subsequential limit of x, which is what we set out to prove. Okay, I see the idea behind this theorem is not too difficult. And I hope you are also able to follow along the technical write-up on this page. Now take a deep breath and we move on to the third theorem for this lecture. The final theorem for this lecture says that every sequence, bounded or not, has a monotone subsequence. So in a way, if we are willing to pass to subsequences, we see that monotone sequences are actually more ubiquitous than we may first imagine. It also says that the monotone convergence theorem from last week may have more chances to be applied than we first realized. The proof of this theorem is a bit complicated. It requires us to start from an arbitrary sequence and extract a monotone subsequence. What we will give is an algorithm to do this extraction. This algorithm has two steps. First, we will try to extract a decreasing subsequence using this idea of dominant terms. This may or may not succeed. But what is neat is that if the dominant terms idea were to fail, then the fact it fails provides us with the necessary ingredient to extract an increasing subsequence using a different method. So when we combine the two steps together, we are guaranteed success. So first, let us explain what is a dominant term. A dominant term of a sequence is a term that is bigger than all subsequent terms. Here, a picture may be worthwhile. Here I'm plotting a sequence. On the horizontal axis is the index of my sequence, with n increasing to the right. Each point represents a term in the sequence. Its vertical position represents its value. The larger the value, the higher up in the picture. So you see that for this sequence, the first term is dramatically larger than all the rest. And since all future terms are smaller, we see that the first term is a dominant term. The second term of this sequence appears to be the smallest value of this sequence. Since even the third term is greater than the second, we see that the second term is not a dominant term. Now let's try to find all the dominant terms. Of course, here we truncated the sequence and do not know what happens to the future. But let's pretend that there are no problems going forward. What the animation is showing is how we compare each term with all subsequent terms. If we find a term that is bigger, we discard it by coloring the term dark green, since it is not a dominant term. If we cannot find a term that is bigger, we record the term as a dominant term and color it orange. As we can see, since the dominant term is bigger than all subsequent terms, it is bigger than the next dominant term that shows up. And hence, the list of the dominant terms are guaranteed to be decreasing from term to term. We also see in this animation that there are occasions where the program has to run for a while before finding out that a term is not a dominant term, that a subsequent term that is larger can happen quite far down the line. And we see that there can be a long skip before the next dominant term is found. Because this list of dominant terms is decreasing, we would have found a decreasing subsequence provided this list is infinite. However, it is possible that the list of dominant terms is finite. Imagine a monotonic increasing sequence. For this sequence, due to it being increasing, there can be no dominant terms. On the other hand, one can also build examples where there are only a finite number of dominant terms before no further ones can be found. In any case, for this example sequence, the picture here shows all the dominant terms in orange, and it is decreasing from term to term. Just to recap what we said earlier, we start by considering the set of all dominant terms. If this set is infinite, then the corresponding subsequence is strictly decreasing, and we found a monotone subsequence. So, the enemy is what happens when the set of dominant terms is finite. Let's talk through what this could mean. First, the definition of dominance is that every subsequent term is smaller. Now, if there are only finitely many dominant terms, this means that after some capital N is reached, no further terms can be dominant. Another way to say is every term after the capital N is the opposite of dominant. Translating this into the negation of the definition of dominance, we see that this means that once a certain capital N is reached, for every subsequent x sub n, we can find an even later x sub m that is bigger than x sub n. Take a minute to convince yourself that this is indeed the same as negating the definition for dominant terms. So, how can we make use of this? Again, we start with an illustration. Here, we are plotting a different sequence. Again, horizontal direction is n, and the vertical direction is the value of the terms. We assume that here we are not starting from small n equals 1 on the left. Instead, we are starting from small n equals capital N on the left, where capital N is the term beyond which there are no dominant terms. And so, for each term, we can find a later term that is even greater. Using this property, we can now build an increasing sequence. We start from x sub capital N. Since there must be a subsequent term that is larger, we find the first subsequent term that rises above x sub capital N. Having raised the bar, we next find the first subsequent term that exceeds that bar, and we repeat. Since we already know that there are no longer any dominant terms, this process cannot terminate. At every point, there will be one more term that is larger to follow. Continuing this way, we build this subsequence of orange terms that is now increasing. Let's finish up by summarizing the picture. In parts 1 and 2 of the proof, we already dealt with what happens when there are infinitely many dominant terms. So now, supposing that there are only finitely many dominant terms, then starting with n sub 1 equaling a capital N plus 1, and continue by picking the first term that meets or exceeds the bar already set, we build an increasing subsequence. This process cannot terminate because we already used up all the dominant terms that are present in the sequence, and so every term has a larger following term. Okay, that's the end of this lecture. See you next time.